Good morning. Thank you very much for the invitation. I've really enjoyed all the talks so far and learned a lot. So I'd like to talk about some upcoming work with Ryan Lanzetta, who is now a postdoc at Perimeter Institute, and Sheng Liu, who has just moved to a permanent position at the Institute of Physics, Chinese Academy of Sciences in Beijing. So I should really say that all the credit should go to Ryan and Sheng, and particularly the main idea and also the implementation is due to Ryan, who is somewhere in the audience. Yeah, so please direct all your hard questions to him. So I'll be talking about bootstrapping one-dimensional line defects and some applications to the three-dimensional Ising model. And there is a very nice parallel story about studying this problem using the fuzzy sphere technology. And I think Yijan will talk about this later in the...
I'm not going to talk about it.
Oh, OK. But I'll show some of their...
I'll briefly talk about that.
OK. So Zhen will talk about it. So whenever I refer to fuzzy sphere results, it refers to this paper. OK. So first, why should you be interested in line defects? Well, as a condensed matter physicist, one reason I'm interested is that if you have a point-like impurity in space, right, in the space-time path integral, it maps to a line defect, and we know that impurity problems can be very rich. A famous example is a Kondo problem of a spin impurity in a Fermi gas, and this problem has really catalyzed a lot of ideas in theoretical physics, including a renormalization group developed by Ken Wilson. So we are hoping that exploring impurities and line defects can more generally can have similar important can lead to similar new interesting physics and techniques. So we'd like to study line defects immersed in more general critical systems described by conformal field theory, because that's the critical systems that we understand best. We search under the light. All right, and I'd like to start with a kind of very simple question, which is related to whether if you have a one-dimensional defect embedded...
Yes? Can I just ask you a question about the motivation and this connection with impurities? If you could study like an array of line defects, would that be like, how close would that be to actual, many impurities in the physical system?
Well, so there are different kinds of setups that we might be interested in. We might be interested in, with the original Kondo physics was about a dilute array of impurities where in a certain temperature range you can just focus on the properties of each individual one where they basically do not talk to each other, and then you just kind of average over them for the bulk properties of the material. But then there are very famous problems, the so-called Kondo lattice model, where you actually do have a regular array of magnetic, well, I don't know if you should call them impurities in this case, but localized electrons with magnetic moment interacting with some conduction electrons. And that's one of the most important problems in modern condensed matter physics, on par maybe with the Hubbard model. And there's not a full understanding of the physics of such a model. But in this talk, I'll be just focusing on a single line defect. Right. So the question I'd like to begin with is, if you have a line defect and your system has some symmetry, can this symmetry become spontaneously broken on the line defect when the bulk is a conformal field theory? So we know that if you have a one-dimensional system, and if this so one-dimensional classical system with short-range interactions, we know that you cannot have spontaneous symmetry breaking. You cannot have long-range order. This goes back to Peierls in the 30s, I think. But we do know that actually, if you have one-dimensional system with power law interactions, and if these power law interactions decay slowly enough, then a long-range order is possible. Now suppose you have a line defect embedded into a bulk conformal field theory, and we ask, now on this line defect, can you get a long-range order associated with your symmetry? So to be very concrete, let's say we have a three-dimensional or d-dimensional Ising model. We tune the temperature to the bulk critical temperature, and then on this line we make the couplings between spins much bigger than the bulk coupling. Okay, and we want to ask when the temperature is at the bulk critical temperature. So this is just a classical StatMech. Can we get long-range order along the line? Why might you think that this might be possible? Well, we have these critical fluctuations in the bulk. If you imagine somehow being able to integrate them out, they induce power law interactions between the spins on the line. So maybe then you can say, okay, this theorem about absence of spontaneous symmetry breaking in 1D doesn't apply, and maybe we can get long-range order. Now, as I'll explain, thinking about strictly integrating out the bulk is actually not a good approach to this problem, but I'll explain how to think about this problem in a better way. But you can also adopt a quantum viewpoint, instead of thinking about a classical problem in d space-time dimension. Think about a quantum problem where you have d-1 spatial dimensions and a time direction. So here, to just illustrate the same Ising model, right? Suppose you have a now quantum transverse field Ising model in one lower spatial dimension, and suppose you tune the transverse field Ising model to criticality. We are now at 0 temperature. And suppose you take one side, and on this side we turn off the transverse field, right? So now on this side, sigma z commutes with the Hamiltonian. This sigma z, by the way, is still coupled to all the other spins via the sigma z interaction. But sigma z on the side, on this impurity side, now commutes with the Hamiltonian. So we have two sectors where it's equal to +1 or -1. Okay. Now let's turn on a very small transverse field on this side, and we can ask, does the impurity spin remain frozen essentially once we turn on the transverse field? We know that if the spin was isolated, right, well, it will not be frozen. You fluctuate between up and down. So that's the reason that you do not get long-range order in 0 + 1 dimensions. But maybe the coupling to the critical bulk can suppress such processes. This is a little bit reminiscent of the Caldera-Leggett type model of decoherence, where actually essentially the same problem of an impurity spin coupled to a bath was studied, and it was studied whether the coupling to the bath can suppress such tunneling processes. In that case, the bath was just a free boson bath, but here, the bath is some interacting system with some locality, right? So all the interactions are local. Okay. So what's the answer to this question? So in principle, if you have a general CFT and you have a line defect, then it turns out that you can spontaneously break the discrete symmetry on the line defect. But for the three-dimensional Ising model, turns out that the answer is you cannot. And we'll actually give a proof of this fact via a new conformal bootstrap method that we developed. Okay, so now to place this a little bit in context, here I'm talking about one-dimensional defect, and possibility of spontaneously breaking a discrete symmetry. Now we know that for continuous symmetries, for an isolated system, the dimensionality of the system needs to be greater than 2 to allow for a long-range order. So we can now ask a similar question about continuous symmetries and two-dimensional defects. Right? You can ask, suppose I have a two-dimensional defect embedded into some CFT. Can I get a long-range order of continuous symmetry on this two-dimensional defect? And the answer turns out to be generically no. Turns out that the closest that you can get to long-range order generically is correlator of the order parameter on the defect that falls off very slowly but still goes to 0 at infinity. And I first found such behavior in the ON model in 3 dimensions, but later Gabriel and Shuyu showed that actually generically you cannot get long-range order of continuous symmetry on two-dimensional defects in CFTs, and that this is actually kind of the closest that you generically get.
So sorry, you would say on a one-dimensional defect with continuous symmetries,
so
it's even less possible?
It's even less possible.
What about this paper by Taroon?
But it's not embedded in a CFT. That's embedded in a free, in a Fermi surface, right? So here CFT is important. Yeah, I'm actually very interested in that problem of a 1 + 1 line defect embedded in a, well, it's not a line defect anymore. It's from a space-time point of view, it's a 2D defect embedded in a Fermi gas. I think Fokker is maybe here. Yeah, so that's a problem studied by Fokker and also Tarun Grover, and there they seem to find numerically and also give analytical arguments that you can have spontaneous breaking of continuous symmetry on the defect. But there you do, the bulk is not a CFT. It has many degrees, gapless degrees of freedom.
So for the case of CFT, there's a proof?
It's basically approved by Gabriel.
But for 2D surfaces, I think it's important.
Sorry?
But for two-dimensional surfaces.
For two-dimensional?
Yeah, but for
Using his asking for lines.
Well, I think for line it's going to be even less.
But I think Coleman's theorem is more restrictive in 2D than in 1D already.
Sorry?
Coleman's theorem is more restrictive already just in 2D than in 1D, in a sense.
Well, if you don't get long-range order in 2D, it doesn't seem very likely that you'll get it.
Qubits are a trivial counterexample. I mean, it's a trivial kind of long-range order, but qubits are trivial qubits, for instance.
Well, the bulk?
Just quantum mechanics, trivial qubits, you can always pick a state.
Well, but then it's decoupled from the...
Yeah, but I'm just saying Coleman's theorem in 2D doesn't even allow for that, because it just pure goes from Wilson to long-range order.
It seems like a discussion between two people.
Yeah, sorry.
let's talk about it after the talk. Yes. So sorry. Okay. So let's come back to our line defects, discrete symmetry, so how should we think about this possibility of spontaneous symmetry breaking on a line defect? Well, let's first remind ourselves why it's impossible for an isolated line with short-range interactions. And this is the famous Peierls argument, right? And the argument is that domain walls proliferate at any finite temperature, right? So if you think about, start with some, so I'm going to again think about the Ising model for simplicity, or Ising-like model, right? And you suppose you start with a perfectly ordered state. Now, okay, you can have ordering where spins point up or down, and then in between you have domain walls, and the energy cost of a domain wall here is finite in the system size. At the same time, you can place this domain wall anywhere along the line, so the entropy associated with a single domain wall scales logarithmically with the system size. Right? So at any finite temperature, the entropy will win over the energy, and you would like to excite domain walls. And that's effectively why the long-range order in 1D is unstable at any finite temperature in a classical 1D system. So how to adapt this argument to a line defect embedded into some high-dimensional conformal field theory? So let's begin by first fixing all the spins on the line defects to be up. And let's compute the free energy of such a configuration. The bulk spins we allow to fluctuate. The bulk is at the critical point. And we compare the free energy of this fully up state to a free energy of having a minus domain here, so 2 domain walls. And we ask, how much free energy does it cost to separate these domain walls? And on general grounds, as I'll also explain in a second, this free energy of the 2 domain walls will also grow logarithmically in the separation. So now we have a non-trivial competition between the positional entropy of these domain walls on the line defects and the free energy cost of separating them. And either one could win, depending on the bulk CFT. As we'll demonstrate in the 3D Ising model, actually the entropy wins and you don't get long-range order. OK, so how to think about this a little bit more carefully? Well, let's again go back to the situation where I just pin all the spins along the line to be plus, right? And the bulk spins now fluctuate. OK, so this is like a pinning field boundary condition. So equivalently, in the continuum model, I can think about starting with the model without any defect at the critical point and perturbing it by integrating the order parameter sigma along this line, right? And I expect that pinning the spins on the lattice will be equivalent to turning on this relevant. This is a relevant perturbation, of course, because dimension of sigma is less than 1. And I expect this kind of theory to flow to a conformal line defect in the infrared. What are the symmetries of this pinning line defect? Well, I expect to have a conformal symmetry associated with translations along the line, dilatations, and special conformal transformations just along the line direction, right? So that's SL2R, one-dimensional conformal symmetry. And then there are the transverse rotations around the line, and then there are whatever reflection symmetries you have in this setup. So I'll call this the pinning field line defect with pinning field plus. Equivalently, there is a conjugate under the Ising symmetry with the opposite pinning field. So I'll call this pinning minus, D minus. OK, now.
So you prove that they exist or not?
They have to exist.
But so then, what are we discussing? So this is breaking.
But this is a situation where you explicitly break the symmetry on the line defect. Yes. They have to be non-trivial because by the so-called G theorem, because this is a relevant perturbation. Yeah. OK, so let's think a little bit more about this, say, pinning plus defect, right? So I can have local operators on the defect. They will organize themselves into conformal towers under this one-dimensional conformal symmetry SL2R, and they'll be primaries classified by their scaling dimension and the transverse spin, right? OK. At the same time, I can think about a junction of 2 line defects of different types, for instance, this pinning plus and pinning minus, right? And then this junction, I also have operators, and these operators also organize themselves into multiplets under SL2R, again characterized by scaling dimension and transverse spin. You might be familiar with such defect changing operators from 1+1 dimension. Cardy introduced them in the context of boundary conformal field theory, this boundary condition changing operators, but they also exist in this setup of a line defect embedded into any dimensional CFT, not just a 2-dimensional CFT. And these defect changing operators will play an important role in our story. OK, So this was a short discussion of general line defects and also about the spinning field line defects. Now, as Slava already, as I already mentioned to Slava, these spinning field defects, I'm explicitly breaking the Ising symmetry on the defect, right? With this turning on this or this sigma field. Now, the question I wanted to ask was about possibility of spontaneously breaking the Ising symmetry on the defect. So let's go back to our lattice model for a second for illustration. Okay, and so I expect that if I can get spontaneous symmetry breaking along the line defect, it will happen when the coupling between the spins on the defect is very large compared to the bulk coupling. So let's begin by just setting the coupling between the spins on the defect to be infinite. Right? So then all the spins on the defect, I can either have them all up or all down. Right? But that's just pinning plus and pinning minus. Right? So then I can think of this line defect in the KD equal infinity limit as a non-simple line defect, direct sum of D plus and D minus, pinning plus and pinning minus defects. Okay, so what are the local defect operators of such a direct sum line defect? Well, I have the local operators of the pinning plus and of the pinning minus. But I also have this defect changing what used to be defect changing operators, these domain wall operators. So before they were not local operators of the pinning field defect, but now they become local operators of this non-simple defect. And the moment I make the coupling along the line finite, these domain wall operators will be induced in the action. And then the question of the stability of this, by the way, this is of course a long-range ordered. This direct sum defect, of course, has spontaneous breaking of the Ising symmetry. The question of the stability of this spontaneous symmetry breaking reduces to the question of whether all the domain wall operators are irrelevant. So we need the scaling dimension of all the domain walls to be greater than 1 for stability.
Sorry, Max, can you say a little more about why these are local operators? I'm confused because in order to stick O plus minus there, the spins have to be plus above it.
Yes.
So how can it be local?
Well, in the situation where you had a pinning field defect, right, where you explicitly pin all the spins to be, let's say, plus, it's not a local operator, right, because you need to flip all the spins, exactly, all the spins below. But in the situation where you have a direct sum of the line defects, it is a local.
Doesn't it act as 0 on the Hilbert space on the plus sector of the Hilbert space?
Is it at 0?
Yeah.
What do you mean by
I'm
that?
saying it's not. Its support is not just at the point. Is what I'm worried about.
Well,
how does it act?
Maybe it will become more apparent when I talk about the quantum picture of this, which is completely equivalent, but just maybe a little easier to visualize. Yeah. So we will prove that the lowest dimension domain wall actually has a scaling dimension less than 1 in the 3D Ising model. So at finite KD, no matter how large, no spontaneous symmetry.
Can I ask a question?
Yes.
If we relax a little bit the setup and we allow for a cusp, this might change this scaling dimension. Is it clear that it can only become more relevant, or maybe one can?
But that's not really a question about the stability of long-range order. I mean, that's an interesting question by itself. You know, what is the scaling dimension when you have a cusp? You can have a cusp with the change of the line or without change of the line type, but that's not relevant for the question of stability of spontaneous symmetry breaking on a straight.
Sure.
On a straight.
But we wouldn't call it spontaneous symmetry breaking if for some theta this dimension is less than 1?
I don't think so, right? Because the question is, you know, you start with this infinite line defect, right? And then you think about domain walls proliferating, right? But then you know, you would need like the line itself would have to become dynamical and kind of zigzag around to be able to freely zigzag. So it's maybe it's kind of in a different universe type of question.
Can I ask another question? So suppose that this operator O plus minus is relevant. So it induces some RG flow.
Yes.
Suppose that RG flow leads to some fixed point. Could that fixed point be also of the spontaneous symmetry breaking type?
I think no, by the G theorem.
But what is the definition? Because you never defined what you mean by which defects are spontaneous symmetry breaking and which are not. What is the criteria?
Maybe it will become a little. I have a comment about this. Right. So here I'll be discussing spontaneous. Okay. I'll be discussing spontaneous symmetry breaking of a very specific type, where at the fixed point for the spontaneous symmetry breaking I have D plus and D minus, and D plus and D minus are just the pinning field defects obtained at the end of this flow. Right? And I'm asking about existence of stability of this D plus D minus defect. And I am saying that it's unstable. Now you could imagine that maybe instead of just making KD very large, maybe you imagine that you make the interactions here along the line very complicated. Maybe you introduce other degrees of freedom, and maybe actually even by explicitly breaking the symmetry on the line, you know, if you maybe break it in some very clever way, you can get a different pinning field defect, right? So one other than D plus. And so let's call it D tilde plus. Some other defect that explicitly breaks the Ising symmetry and is stable. And then, you know, you can form direct sum D tilde plus and D tilde minus. And I cannot say anything about stability of such defects. And in particular, the bootstrap will not say anything about the stability of such defects. But what I'm saying is that for this pinning field defect, we can show that it's unstable. This simple pinning field defect that's obtained by a flow of a sigma.
Wouldn't that require not an Ising odd operator of dimension less than 1 in addition to sigma?
It would need to be at some strongly coupled, right? So it will be some defect not obtained from the transparent defect by an RG flow.
I think a bootstrap in principle can apply to any defect.
It can apply to any defect, but the island that we find is for this particular defect. There is like a whole continent, and you know there could be other pinning field defects in principle living in that continent, and we cannot say anything about their stability. Okay.
I just couldn't see from this angle. Can I go back? Okay, what's less than infinity? And what's written on the very left?
If there's coupling along the
Oh no, it's not it's not the board that's
if the coupling along the defect is less than infinity, then this domain will say immediately indeed.
Also, the deformation that cause the propagation of segments, negative segments, should it be O plus minus?
And O minus, and O minus, and both, of course. Just by hermeticity, or well, yeah. So maybe this quantum perspective is also helpful. So go back to the transverse field Ising model. Remember this pinning. We had this spin where we turned off the perpendicular field, the transverse field. The sigma z of this spin commutes with the Hamiltonian. We can fix sigma z equal +1 or -1. When it's +1, that's the D plus defect, the pinning plus defect. When it's -1, it's the pinning minus. Right. So literally, the Hilbert space is the direct sum of the Hilbert spaces of these plus and minus defects. And now if I turn back on the transverse field sigma x, right, then well, that flips the spin. So really, you do get this domain wall in space time. And I think that's the answer to your question, John, right? It's really a local operator, right, that induces these spin flips. Okay. Now, as I said, we're going to prove that this scaling dimension of this operator, of this domain wall operator, is smaller than 1 in the 3D Ising model. So then the spontaneously broken line defect is unstable. So where do things flow to? And the very natural guess is that it flows to the transparent defect, to h perp on the defect equal to h perp in the bulk. Well, so kind of a check on that is that if you start with a transparent defect and you perturb by symmetry allowed perturbation, the lowest one is epsilon. Epsilon scaling dimension is greater than 1. So it's irrelevant. So at least this picture of a flow from the d plus d minus to transparent is self-consistent. Okay, so my main interest will be in the 3D Ising model, but let me briefly remind you what happens in the. You can ask the same question in the 2D Ising model. So let me remind you what happens there. So there, if you have a pinning field defect, it actually splits the bulk into two uncoupled halves. On each boundary, you expose the pinning field defect. Now, you can ask, what's the scaling dimension of the domain wall? Well, the domain wall has to flip both boundaries here. So it's a domain wall is a product of domain wall operator on the left boundary and the right boundary. Each one has scaling dimension 1/2 in the Ising model. So overall, this domain wall on the line defect has dimension 1. So it's marginal. And it turns out to be actually exactly marginal. And it induces a line of defect fixed points where you, on one end of the line, you have this spontaneous symmetry breaking boundary condition. On the other end of the line, you have you again cut the system into half, and you have free boundary condition on either edge. And in the middle, you have the transparent defect. Okay. So here again, the spontaneous symmetry breaking is only at this end of this line of fixed points, and once you move away from it, then the Ising order parameter has a finite scaling dimension along the on the line, so you don't have spontaneous symmetry breaking. Okay, so let's go back to three-dimensional Ising model and line defect in the three-dimensional Ising model. So our main target is the scaling dimension of these domain wall operators joining the pinning plus and pinning minus defects. Okay, so there are different methods you could try to attack this problem. One method is perturbative. You could use the 4 minus epsilon expansion, and actually Subir and Andrea Ale were the first to develop this 4 minus epsilon expansion for the pinning field defect, and there's been also subsequent work expanding this by Gabriel Como, who is in the audience, and Zohar Kamargotsky and Mark Mazet, and also by Yin-Chen He with the above authors. So
Can I just ask a question about the previous slide?
Yeah.
So you didn't have, maybe I didn't understand what was on the slide, but you don't have the 2D Ising with the transparent defect anywhere on this line.
This is the transparent.
Okay, sorry.
Yeah.
Thanks.
Okay, so until recently, this was the best. This 4 minus epsilon expansion was what gave us most information about the spinning field defect and about operators on the spinning field defect, and Monte Carlo, by the way. But now we want to develop a method to bootstrap this line defect, and the question is how to do it. So well, let's first very quickly remind ourselves about bulk conformal bootstrap. This audience hardly needs needs a reminder, but let me very quickly go through it, right? So in the bulk conformal bootstrap, we have bulk operators with their scaling dimensions. We have the operator product expansion, and we have the composition of a 4-point function using the operator product expansion, and we have the crossing equation, right? Well, the crossing equation, let's say for simplicity, for scalars of for four identical scalars, involves operator product expansion coefficients squared times conformal blocks. And in a unitary theory, these OPE coefficients are real, so the squares are positive, and then you can use linear programming, or more generally for mixed correlators, semi-definite programming techniques to place constraints on the spectrum of operators, delta entering this crossing equation. So this positivity is very important for the implementation of the bootstrap. Okay, so now you start ask the question: if you have a defect, how do we bootstrap defects? You know, this is actually a very general question for defect of any dimension, not necessarily even for a line defect. So you know, one approach would be to say, okay, let's think about correlation functions of bulk operators in the presence of a defect. And actually, a 2-point function in this case is already not fixed by kinematics. Okay, so then you could say, again, there are two ways to expand out this 2-point function. You can either think about the bulk to defect operator product expansion, and then we just take the correlator of two defect operators, and that's one side of the crossing equation. On the other side of the crossing equation, we can think about first fusing the bulk operators, and then you take the expectation value of the resulting bulk operator in the presence of the defect. Now, in this channel, we do have positivity, because we have a bulk to boundary operator product expansion coefficient squared. But in this channel, we don't have positivity, right? We have expectation value of the operator in the presence of the defect that doesn't have a fixed sign, and we have the OPE coefficient between the two bulk operators that also doesn't have a fixed sign. So there is no positivity in this channel. So that's really the problem plaguing bootstrap of defects. You could take a different approach. You could say, well, let me forget about bulk operators. Let me just bootstrap correlators just on the defect itself. That's fine. You know, all the rules of bootstrap apply. The only problem is that how do you know that this is a defect embedded into the bulk? So this generally doesn't constrain your correlators very much. So for line defects, we seem to have been able to partially alleviate these problems, and at least for a certain type of line defects that can end. So the key idea turns out to be to consider ends of line defects, and I think the first perhaps implementation of this idea in Bootstrap has been in this paper by Ryan and Lukasz Witkowski a few years ago. There they focused on line defects where the line is topological and it's only the endpoint which is non-topological. But turns out that this idea can also be applied to line defects which are not topological as long as they can terminate. Okay, so again, you know, if you have an endpoint of a line defect, you can think of this as a defect changing operator between trivial line and a non-trivial line. These endpoints will again organize into towers under SL2R symmetry. So the main idea that we'll use is we'll study expectation value of, if you wish, partition function of two defect segments like this in a collinear geometry, and the defects can be of different types, A and B. Why is this a useful geometry to consider? Well, let's just first, you know, let's play this out for the Ising model, right? So let's first say we have two pinning field defects of the same sign, right? Then if I think about bringing x1 close to x2, that segment becomes very small, so you can think of it as a bulk operator. Same here. Alternatively, if you bring x2 to x3, then the gap in your segment becomes very small. You can think of that just as a defect operator. So then the crossing equation here, where I think about these two different fusion channels, relates the bulk operator spectrum to the defect operator spectrum. You can also think about two segments of opposite pinning field defects, right? So in this channel, again, you get bulk operators, but in this channel, you get domain wall operators. So you can learn something about the domain wall operator spectrum. And you can also mix with bulk operators like this, right? So again, in this channel, you get bulk operators. In this channel, you get different endpoint operators. So for the Ising model, we study the system of these, I think 7 or maybe 9 correlators. Okay, how do we study it? Well, all of these correlators, the operators are in the collinear. A collinear, that's important. So they're all on a line. So we have the one-dimensional SL2R conformal symmetry, SL2R symmetry acting on these operator positions, and we can just apply one-dimensional bootstrap to this problem.
Can you remind again the nomenclature F00 plus
Yes.
F0 plus? I'm confused.
Yes. So this, for these line defects, right? There will be a spectrum of defect endpoint operators. And here, this operator refers to the lowest dimension defect endpoint. Right? Just end with the lowest dimension operator.
But why do you write sometimes 0 plus and sometimes 0 plus 0?
This is some nomenclature that we introduced. That this is, you kind of think about the this time direction here. And it's between trivial transparent, which is 0, and plus, and then here between plus and transparent, and same here. Yeah.
And if it's blue line, then it's what?
It's minor. It's opposite sign of the symmetry breaking. Okay. Couple of comments. So this one-dimensional this bootstrap surprisingly allows us to access the so-called defect G parameter, G function. So G function is defined as the expectation value of a circular defect with the proper subtraction for the cosmological constant on this defect, and it was shown by Gabriel Koma, Zahar Komargotsky, and Avia Raviv Moshe that this actually is a RG monotone. It decreases under defect renormalization group flow, same way as, say, the bulk central charge decreases in 2D and 4D CFTs. Okay, now it might be surprising that you can access this quantity using this collinear geometry, but well, first of all, you know that a circle is conformally equivalent to a line. Yeah, so the reason is this. So if you normalize these defect endpoint operators to identity, and you think about the operator product expansion like this, where you fuse them to defect operators, then on the right you'll have all defect operators appearing, but in particular you'll have the identity defect operator. And turns out that the coefficient of this identity operator is exactly 1 over G. And the way to realize this is to think about a circle with a small arc cut out like this, and apply the operator product expansion here, right? You'll end up with a full disk that has an expectation value, full circle which has expectation value G, and it will cancel with the 1 over G here to give you the normalization 1, which is what we have for the expectation value of this arc. Okay, what else? Now, because our bulk is 3D Ising, and we know a lot of information about 3D Ising from bulk conformal bootstrap, we can put in all of that information by hand, right? So, for instance, we know the low dimension operator spectrum of 3D Ising to very high accuracy. So these numbers we just hardwire in, and then we've also put in the rest of the low-lying spectrum. I think we put in all the operators up to dimension 6, and for some of them we have rigorous error bars on their location. For some of them we have non-rigorous error bar, but anyway we are always very conservative, and we allow for the error bars on the location. So all of that information is put in, and remember the bulk operator spectrum appears in these fusion channels here. Another observation is we are using one-dimensional conformal bootstrap, right? So we are expanding everything in terms of primaries of the SL to R conformal group. Now, in these fusion channels, we do have some bulk operators appearing, and it turns out that some of the SL2R primaries are actually descendants under the full bulk conformal group. So there is kind of branching rules. So, for instance, if you have a bulk scalar phi, then this operator is, of course, a bulk descendant, but it's a SL2R primary. And that means that we know...
Could you remove your arm from the microphone? No, not the microphone. Your arm is on the microphone, the wire.
I see, sorry. Yes.
Maybe the zone 2.
Okay, let's see if this works. Oh, okay. So we know the OPEs of these bulk descendants with other bulk operators in terms of the OPEs of the primary, and we put that information in for the low-lying part of the spectrum. So in particular for these descendants of sigma epsilon and epsilon prime, we of course, if you have this operator phi 2 here, we cannot fix this 3-point function of a line segment with it in terms of the 3-point function of a line segment with the bulk primary phi, right? Because there is this kind of second derivative here in the transverse direction, and there is kind of nothing that you can do about it. But this information we put in for the low-lying operators. Okay, so with all of that, of those remarks, let me just show you our results. So here is the plot that I'd like to concentrate on. So on the horizontal axis is the scaling dimension of this defect endpoint operator. We always, in our system, remember, we put in the lowest dimension defect endpoint here at the ends. So that's the scaling dimension of that operator. And on the vertical axis, we have the ratio of OPE coefficients of a line segment with either sigma or epsilon. And you see, and the only assumption that we make is that the spinning field defect is stable, right? That so the explicitly symmetry broken defect, that all the local defect operators are irrelevant. And we see that we get this island. And we believe from epsilon expansion and also from the fuzzy sphere results that the physical pinning field defect lives inside of the island. And then there is a continent, and the continent seems to recede as you increase the truncation lambda, but I won't have much to say about it. Anyway, so the island, so this is like bootstrapper's dream, right? That you got an island. Now, this is with minimal assumption, you already get an island, just the stability of the pinning field defect. If you crank up your assumptions, guided either by epsilon expansion or by fuzzy sphere, so you make more aggressive but still rather conservative assumptions about the defect spectrum, you can shrink this island quite a bit, and you can become now competitive with the fuzzy sphere results. So you can kind of have some rough results from fuzzy sphere, put them into Bootstrap, and then improve on the fuzzy sphere results. So the fuzzy sphere is this, it's maybe not very visible, but it's this light beige rectangle, and then with conservative but non-minimal assumptions, we can reduce the size of this island to this dark nugget here.
Isn't this a bit surprising? So this dimension is actually 0.1.
Yeah.
So it's super. So there was never any doubt that it was going to be relevant.
No. But this is the endpoint. This is not the domain wall.
This is the endpoint.
Now I show you the domain wall. Okay. Right. So let's scan over the size of this island here, and let's find what is the bound on the domain wall. Again, this is with the minimal defect assumptions that the pinning field defect is stable. And you see that everywhere in the island region, the scaling dimension of the domain wall is smaller than 1, but it's actually it's not 0.1, right?
So where's the island region here?
Is this entire horizontal range, right? So if you see, this is 0.9 to I don't know 12 or something like that. 0.19 to yeah. So based on this and the assumption that the physical defect lives inside of this pinning field defect lives inside of this island, we conclude that there is no stable long-range order, or more precisely, that the pinning plus pinning minus defect is unstable to domain wall proliferation. Okay, so this is this caveat that you could perhaps there are other pinning field defects with the same defects with the same symmetry that live somewhere in this continent, and then we cannot say anything about the stability of this spontaneous symmetry broken d tilde plus d tilde minus defect. That's what I already mentioned. Okay, so here are the generic bounds over the island size on the domain wall operator. We also have generic bounds with these minimal assumptions on other operators. So this is the defect, lowest dimension non-trivial defect operator, and this is the next endpoint operator. And you see that they have some nice sharp kinks, and the fuzzy sphere results are these rectangles that seem to overlap with these kink locations. We can also look at the G function, right? And with minimal assumptions, we just get this big egg here. But something important about that big egg is that G is always smaller than 1 and greater than 1/2. Why are these numbers important? Well, remember the transparent line has G equal to 1, and G has to decrease under RG flow. Well, the pinning field defect is obtained from the transparent one by turning on sigma. So G has to be, of the pinning field defect, has to be smaller than 1. Okay, and it's always smaller than 1. It also has to be larger than 1/2, right? Because we are guessing that there is a flow from the spontaneous symmetry broken defect, pinning plus pinning minus, to the transparent defect. So that means that G has to be greater than 1/2. Everywhere in our egg, G is greater than 1/2. Now, if you, again, turn on non-minimal assumptions on the defect spectrum, but still rather conservative, you can shrink this egg to this little nugget here. You see that the nugget has a kind of a kink here. So we think that the physical theory is near the kink. And again, the rectangle is the fuzzy sphere result. So again, by making non-minimal assumptions, let's say motivated by epsilon expansion of fuzzy sphere, you can now improve on the fuzzy sphere results. Okay, and if you do G minimization and extract the spectrum near this kink of the nugget, you actually get first few operators, and which agree. So the dashed, well, I think this pink lines are the fuzzy sphere, and for the low dimensional operators in various sectors, over the close to this kink of the nugget, we get agreement between the fuzzy sphere spectrum and the spectrum extraction. So we can compare with these non-minimal assumptions on the defect spectrum. We have for some quantities we have rigorous bootstrap bounds under these assumptions, and then we have also values for various operator dimensions from this G minimization, and they are in very good agreement actually with the fuzzy sphere. For some things we can do better than the fuzzy sphere. For some things maybe we have similar accuracy. Okay, so I think I'm coming towards the end of my talk. So we have this new method to bootstrap line defects. It seems very successful for the 3D Ising model. How can we improve on it? Well, maybe we can put in more information about the bulk conformal symmetry, right? So here, as a part of my bootstrap system, I have the 4-point functions of pure bulk operators, and these bulk 4-point functions in the collinear geometry can also be expanded using not just 1D blocks but also 3D blocks. So maybe if we put in the expansions in terms of the 1D blocks, which is what we're already doing, and also separately an expansion about the 3D blocks, and link the low-lying part of the spectrum, maybe we can improve on the bounds. Yeah, and then the other comment is that, of course, we would like to extend this to other conformal field theories, and I think the dream is to study Wilson line defects in gauge theories. And maybe this will be a way to not only place constraints on the defect spectrum, but also learn something about constrain the bulk spectrum in some way. Okay, so I think that's all I have to say.
Maybe you shouldn't. So some parts of the correlator in the previous slide. So those correlators, the 4 correlators on the right, they are basically known. So there's no need to bootstrap them again. I mean, you can just stick them. The whole correlation function is known from previous bootstrap studies using 3-dimensional analysis. So it's kind of wasteful to redo the analysis. It's not clear how to interface the information, but we should be able to take those correlators from previous analysis and just stick them into the analysis and bootstrap everything else.
Yeah, so I think for positivity of the 1D bootstrap, right? We need those OP coefficients in the bulk channel appearing as like lambda squared. So in principle, we could take the 3D bootstrap and we could. So we already fixed the values of some OP coefficients just by hand. So maybe we could fix more. We just didn't. We were a little wanted to be a little bit conservative about. So we only, I think, fixed these OP coefficients, but we can probably fix more. When you say that the full 4-point function is known, you mean that?
No, I mean it's known to because there were some. For example, there are some other bootstrap studies which study those 4 correlators and adding, for example, correlators of stress tensor and whatnot, and I mean they reach humongous accuracy. Now it's kind of unreasonable that now you have to redo everything from scratch. I mean, I don't claim that I have a complete proposal, but I hope there is a way to recycle the results of those studies in some.
No, but I think
meaningful way, which would save the effort.
Well, I just wanted to say that I think that all these defect crossing equations augment the bulk crossing equations. So they should really all be tied together, and it leads to, in principle, stronger constraints both on the bulk and in the defect.
But maybe for the 3D Ising, because we know the bulk so well, we can recycle that information. But for maybe like for gauge theories, the hope is that maybe this will help us isolate islands for bulk operators.
That would be great, because I mean, when initially Leonardo Rastrelli, Balf Maurice and so on, they started using this, doing this boundary defect bootstrap, that's what they hope. Somehow by doing this, they will learn something about the bulk. But this, so far, this hope has never been realized.
Right.
Information always flows in the opposite direction. So if you find an example where it flows the other way, that would be great.
Yeah, I think maybe the reason that we are modestly optimistic, right, is that in some kind of large n or whatever limit, these endpoint operators, right, they're just like free fields. Yeah. So they have like, whereas the bulk operators are some composites, so maybe this will help you, but who knows? One has to try before. Yeah.
Are there line defects that can't end?
Yeah, like let's say pi flux defect in the Ising model,
and so
in 3D Ising model. Those cannot end, so they cannot be bootstrapped in this way.
Can you include them by putting them on the whole line and then adding on to them?
Well, so you can do this for them, right? You can. You can do this. That's totally fine, right? And you can also, in principle, this is valid, but it just you cannot use positivity. You cannot use linear programming.
I guess could you do the thing you're doing, but with the unendable line defect coincident with your axis?
Well, so I think the power of our methods is that we have the segments where the endpoints fuse to bulk operators.
In the other slide, could you get positivity when considering pairs of line defects? What you need is a complete set, right? You need all the crossing relations.
Yes.
Yeah, so I mean, could you, if you considered 2 line defects, so you would have a full set of crossing relations, would that give you positivity?
But you want to have another line here.
Well, I have 2 types, A and B, and I want to have all possibilities, right? And then when you have all possibilities, you have a matrix, and that's how you get positivity back, right?
Right.
So if you had 2 pairs of defects, would you then have another sector?
2 pairs in space or in?
Well, you have 2 types of operators, right? A and B.
Yes.
And as if I understand it, you get positivity by considering all possible A and Bs. That's basically.
No, it's possible to consider this, Rich. Yeah, people have thought about this, but these pairs of defects that you have in mind, then you have to come up with a way to do OPE for defects.
Right, so you end up some new, you have some new
never
OPE.
been understood.
Yeah, okay, so you have some new data you have to put in.
You want to put in another line?
Another line.
Yeah, exactly.
In 2 dimensions, it's understood from the annulus partition function to some extent, but in higher dimensions, it's hard to see.
People are starting to think about this defect fusion in higher dimensions, but
they are starting since 20 years. So very slow start.
Well, Yifan has some results, right, in Zohar.
Something about the interaction between defects, is that the problem?
Yeah. I guess your talk was about the fusion of defects, right?
But only in some very particular setup, a very particular geometry. Yes?
Very naive question. You are hoping to do something with gauge theories. The 3D Ising model is dual to a Z2 gauge theory. Can you reinterpret what you did in that language and learn something interesting?
I don't think you can learn anything. Yeah. Also, I mean, you can reinterpret, but I don't think you can learn anything yet. And that's a very kind of simple. I mean, everything is kind of all the additional physics is kind of corresponding to gap sectors right there. So.
Well, except that the reinterpretation gives you Wilson loops, which you would maybe be able to figure out by using the duality.
Well, there the Wilson loops are, the interesting thing there, right, is the Y zone or the pi flux defect, right, which is the pi flux defect of the Ising model, which this method doesn't apply to, unfortunately.
Okay, one more question and we go for break. Yeah.
Have you thought about other combinations of the any defects? Like don't know, 2 of one and 1 of the other or something? You could ask the analogous question.
Oh, more than 2 segments, or?
No, I mean, so you asked the question you answered here is about the stability of what happens when you put d plus and d minus on top of each other. You could ask an analogous question for arbitrary numbers of each of them.
I think people have played this game in 2D. Trying to remember the name of the person who, maybe it will.
I guess whenever you have an equal number of the two, it still has a symmetry interpretation.
But then there is some extra degeneracy, right? That somehow you don't expect to be here. At least you could imagine that the symmetry protects the degeneracy, but there are other kind of identity operators that can lift the degeneracy.
Okay, well, thanks, Max. Thanks.